can have like a 3-piece subshell, as an example. And then the last thing is you've got the individual orbitals within the sublevels. All right, so that's just an example. So just so you know how the periodic table is broken down. Does this make any sense at all? It's just taking broad, not so broad, very specific. Okay. So the quantum number n represents what shell an orbital is in. Okay, the quantum level L, or quantum number L, tells you which subshell it could be in. Okay, and then the quantum level number plus or minus a half, it doesn't tell you exactly which orbital it's in, but it represents a quantum number within an orbital. And the periodic table is broken up into that structure. Right? You've got the P block, the F block, the D block, and the S block. Right? These are all sublevels within the periodic table. So you're going to need to know what a subshell or what a shell is, what a subshell is, and what an orbital is. Like how do those two? How are they different? Question. Okay, how many electrons can be placed in the 3D subshell? 10. Right, exactly. So I've got a 3D subshell. I've got 5 orbitals. Each orbital holds 2 electrons. Right, so I can fill in 10 electrons in a 3D subshell. How many electrons could I hold in an infinity D subshell? Still only 10. So it doesn't matter how high the quantum level n is, a D subshell will always only hold 5 orbitals. And each orbital within that subshell holds 2. So each D sublevel, whether it's 3D or infinity D, will only hold 10 electrons. Here's a nice brain teaser question. Are orbitals real? They're not. I'm teaching you stuff that's not real, but it's a mathematical model that seems to fit every experiment we've ever done. Okay, so orbitals are just a part of the quantum model, but they're not. No one's ever seen an orbital. We have not been able to look inside an atom and there's the p orbital. I mean, we haven't been able to see that, right? But it's just all part of the model that helps explain the experimental evidence of the line structure that we see, especially the spectroscopy part of our experiments. We see that all the time. Okay, so the idea of quantum mechanics is just that. It's an idea. Okay. So there's another heavyweight in quantum mechanics. Last name is Pauli. And so there's an exclusion principle that says that the existence of an electron in the atom is described by its own unique set of quantum numbers. Okay, so in other words, you cannot have any one electron that has the same set of quantum numbers as another electron. So imagine going to a baseball stadium and finding someone with a ticket that has the same exact seat number as you. Would there be a problem? Yes, there'd be a huge problem. Okay, so by analogy, the electron has its own ticket number to the atom, and you cannot have the same ticket number for any 2 electrons. Each electron has to have its own unique ticket number, or set of ticket numbers. Okay, and that ticket has a set of 4 quantum numbers unique to that electron. Here's the sample problem. List all the possible sets of quantum numbers for a 5p electron. Okay, so I've got columns here. So for 5p, what is my n value for 5p? 5. What is my L value? It's going to be 1, right? Because it's a p orbital. So I think you're starting to catch on, right? N and then L. Okay, now for m sub L, it's not asking me about a specific p orbital. It's not saying 5px, 5py, or 5pz. Not that really matters anyway, because even if it told me x, y, or z, it doesn't matter which m sub L value goes to which one of those orientations. So what are the possible sets of m sub L? And -1, 0, and 1. And then what about my m sub s? What values can those take on? Right, positive 1/2. Now, I'm just going to go ahead and write positive 1/2 all the way down. Now, what I can do is I have 3 distinct sets of quantum numbers, right? So, these 3 sets differ by their m sub L value. Could I write another set that differs by some other number? Have I taken into account all the m sub s values? No, right? So I can write another set where I have negative 1/2. And there are my 6 unique sets of quantum numbers for an electron in the 5p subshell. 6 distinct sets of quantum numbers. Let's look at the p subshell. Oh, that was a 5p, but I could just as well look at a 2p. Right? I've got 6 electrons. Each of these 6 electrons in this p sublevel are represented by 6 unique sets of quantum numbers. What if it said 2p? How would that change that set over there? If this was a 2p, the only thing that would change would be the quantum number 2. And that'd be it. What if it was infinity p? The only thing that would change would be infinity here. Hmm?
So what if you were to say that we like half full electron?
Right, so you're almost asking, what if we only had a 2p sublevel that was only half full? That means that only 3 of these 6 quantum numbers sets would be used. Okay, it's just like when you're filling into the baseball game, not all the seats are filled right away, but the seats are still there. Right, they still have their own ticket number. Somebody's on their way to the game with that ticket number, they're just not there yet. So when you're filling orbitals with electrons for a given element, sometimes the seat is there, it's just not filled. Right? Sometimes the games don't sell out. Okay, for hydrogen, there's only 1 observer, not very much attendance. But for say element number 118, un octium, okay. For element 118, there's a lot of people there, right? There's a lot of electrons filling in the orbitals at that point, and they're taking up all these tickets. All right. Let's skip this one for now. It's actually in your problem solving. We can do that. Okay, so last thing I need to talk about today. First, the notes. Any questions about this? What I suggest you do is, I'll upload the video. I'll do that after probably tomorrow. But try to go through your notes today, even later today. Just read through them. Maybe watch the lecture again. Because if you don't look at this for 5 days, it's going to be really hard to connect the dots again. Okay, so just keep connecting the dots. Okay. So there are 3 different representations of atomic electron wave functions. the wave function itself has no physical meaning. Okay, so I gave you a handout. I think so I gave you a handout, and there's this page here has some onion-looking shape thing here, and then there's a diagram right there. So those are the actual wave functions that have been determined as solutions to the Schrödinger equation. Now, what they often do is they will square that wave function to give it meaning. Mathematically speaking, what kind of functions give you wave behavior? How many of you have taken trig before? Sine, cosine, tangent, you know. If you looked at the actual mathematical functions that have been representing solutions to this Schrödinger equation, if you see them, they all have some form of sine or cosine functionality built into them. You don't need to see them, I'm just telling you right now, they're all cosine and sine functions. So the wave function looks like something like this. Now, if you have an electron that's behaving in this way, and when I say behave, I mean it exists as a wave, and it's constantly surrounding the nucleus as a wave. I mean, imagine if you were an electron. You're not a particle in the usual sense. You've got mass to you, but you're spread out across all this volume of the nucleus, and you exist as a wave contour. Okay, and so that's what this slide's about here. Let me show you this other one. Okay, imagine if you existed as this. Imagine if this was you. Like, you're no longer you, you're like a wave spread out. This is how you exist. You exist as a cloud, and you're moving in space, and you have this wave function to you. Okay? But does this have any physical meaning? And it doesn't. Right? This means nothing to us. Okay? So that 3D picture of the wave, this is like taking a cross-section of that wave. Imagine if I took a cross-section and I sliced it right through here. And what you would see would be something like, you'd see something like this, right? If you took a cross-section of that picture. That's really weird, right? It has no physical meaning. We don't really care about that. But what we do care about is the square of that wave function. If we square all the negative values in this function, or if we just square it, what happens? We get this. We get that, right? So there are no more negative values, everything's positive. Okay. And so this top one's the wave function. This second one is psi squared. It's the square of the wave function. And we call that the probability density. Now, this is still just a cross-section. If we could take a wave that's now encompassing the entire nucleus at all angles, and if we took all of those wave functions, took all those values and then added them together, if we summed up all the wave function squareds around all the angles, we would get something called the total probability. And this is what we are most concerned about. this up very well. To be honest. There we go. Okay, if we sum all these together, it starts getting bigger and bigger and bigger the further you go from the nucleus. These, mathematically speaking, all of these places where the wave function crosses zero represents a zero probability of finding an electron away from that atom, away from that atom's nucleus. So imagine here we have the nucleus. All right, so we have the nucleus there, right? Okay, all of these places where I have zero value for sine and cosine and such, these represent nodes. Okay, and nodes represent distances from the nucleus where electrons cannot exist. Okay, they are places where we have no chance of ever finding an electron there. So these are basically, imagine an atom, okay, where you're cutting it in half, and you have an onion represent, if you cut an onion in half, you see rings to it, right? And what's in between those rings? There's kind of like nothing there, right? That's kind of like what an atom is, right? It's got regions of space away from the core of the atom, away from the nucleus, where there is nothing there, right? There's no electron density or anything. Okay, so here's a nice diagram of a 2s and a 3s orbital being cut in half, and then also being cut in half again. So what's not showing on this slide is the original wave function. So I kind of wrote an original wave function here. Now for a 3s orbital has two nodes to it. And it turns out that there's this equation. This is not given to you in the book, but it's how I learned it, so I'm just giving it to you. So the number of nodes for any orbital is given by the quantum number n minus the quantum value L minus 1. And these represent the number of nodes away from the nucleus. Some textbooks and some professors will include the nucleus as a node. I don't do that. I just include the regions of space away from the nucleus that have zero electron density. So for a 3s orbital, check it out. N is equal to what for a 3s orbital? 3. L is equal to what? For any s orbital, L is always equal to 0. Okay, and then minus 1. So 3 minus 0 minus 1 gives me 2 nodes. And that matches these 2 nodes in this picture. Okay? And look at this diagram here. Notice how there's regions of blue and then white and then blue and then white. So the regions of blue are where the electrons reside, and the regions of white are where the electrons are not allowed to reside. Right? They're mathematically impossible. It's mathematically impossible for the electrons to occupy that specific distance from the nucleus. So mathematically speaking, we know that there are portions of this function where there's zero values, right? And mathematically, that tells us the electron can't occupy that distance from the nucleus. So the y-axis is the probability, and the x-axis is the distance. Distance from nucleus. But again, the wave function itself has no physical meaning for us, because how can an electron have a negative probability and a positive probability? You know what I mean? You know, you either have a probability of finding the nucleus there, or finding the electron there, or you don't. You don't say I have a negative probability of finding an electron. Okay, what's the probability of me finding money in your purse or wallet? Well, if you don't carry cash on you, I don't know. Right? Some people don't carry cash. But let's just say you had no money in your purse or wallet. Would you say that there's a negative probability of finding money in your purse or wallet, or would you just say that there's just zero probability? Yeah, you can only have zero probability. You can't have negative probability, right? So it's the same thing with finding an electron in some distance around the nucleus. Right, there's either zero probability or something above that. All right. Okay, so what if I took the total probability, which is just the sum of all the wave functions squared, around 360 around the nucleus in all angles. Okay. So what if I did this? So here is a 3s orbital. Okay, it's got two nodes. Okay, so this was originally a positive value, and then the negative value, and the positive value. What if we were to rotate this? Okay, this is really hard for me to draw, but I'll attempt to draw it. What if I do this now? Okay, and rotate this entire graph. Do this. I'm crazy for trying to do this right now, but it is that cool. And then what if I rotate this function again? Let's see. Can we write it upside down? I think we can. Let's see. Boom, boom. It'd be like this. Let's see. No, it won't be like that. It's going to have to be like this, right?
Yeah.
Something like this. Boom. Okay. And then this will be, I don't know, it'll be something like this. Anyway. Alright, I can't do this. But let's just say we rotated this around and you now have this partial ring. It's really hard for me to visualize this now. Okay. And then I'm going to do this again for the ren. If I rotate this graph 360, I can get a cross-section of a 3s orbital. Okay. Talent is being stretched here. Okay. So if you take this graph and rotate it all the way around, you would get something that looks like this. Can you see that? Okay. So what the graphs represent is just along one axis away from the nucleus. Okay, but what psi total really is, it represents is a cross-section of the whole rotation around the nucleus of the atom. Right, so the nucleus is, you got the nucleus in here with a bunch of protons and neutrons, right? And then you got these regions of electron zero density. Right, so you can say node 2 and then node 1. So that picture in the PowerPoint slide attempts to show that. I'm just trying to draw it in my own way. Okay, and then so if you cut an s orbital in half and looked at the rings, these kind of sort of represent Bohr's orbits. They represent the shells, right? But for each orbital that gets bigger, like for a 4s, what do you think a 4s would look like? So this is a 3s orbital. What do you think a 4s would look like? It'd look just like this, but it would have one more blue structure to it, right? It would have one more ring. So again, this is kind of like taking, this is the 4s, now it's bigger, right, than the 3s, bigger atom. And it's kind of like taking, if I took the y-axis or put an axis on it, it'd be like this.